Hello and welcome again to Chem in 3. Today we look at chemical equilibria. And when you hear the term equilibrium, you might think of a balance like this, where each side has exactly the same mass and it balances off. But in chemistry, each side of a chemical equation does not necessarily have to have the same concentration of reactants and products for the reaction to be in chemical equilibrium. And we should also note that when a chemical reaction is in equilibrium, both the forward and the backward reactions continue to occur, but the concentrations of reactants and products remain the same. This is known as a dynamic equilibrium. Let's move in and take a closer look.
The Haber process, involving nitrogen and hydrogen to produce ammonia. And here you can see that 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia, with reactants and products in the same state. This type of reaction is termed homogeneous because reactants and products are in the same state. The reaction is also exothermic, with heat being released from the system, as bond making produces more energy than is consumed in bond breaking. With this exothermic reaction, we can look at it as heat being a product of the reaction. And then, in keeping with Le Chatelier's principle, which says that if a system in equilibrium is subjected to a change or a constraint, then the system behaves in such a manner to remove or to oppose that constraint. So given Le Chatelier's principle, then we can say that if heat is added to this system, the reaction would move from reactants back to products, or in the reverse direction. If we added pressure to this system, then the reaction would move in the forward direction, moving from where you have more volume to where you have less volume, bearing in mind that 1 mole of any gas at a given temperature occupies the same volume, so you have 4 moles of gas becoming 2 moles of gas. So an increase of pressure will push the reaction forward, again in keeping with Le Chatelier's principle. If the concentrations of the reactants were increased, that too would push the reaction forward. In the study of equilibria, we also consider Kc, the equilibrium constant, a value which at equilibrium takes the concentration of ammonia squared, because you have 2 moles of ammonia, divided by the concentration of nitrogen and multiplied by the concentration of hydrogen to the power of 3. This value stays the same at equilibrium and is independent of changes in concentration, pressure, and of course the addition of a catalyst. But with a change in temperature, the value of Kc could change. In the case of this reaction, the Haber process, with the reverse direction being favored, then the concentration of reactants would increase at equilibrium, and the value of Kc would become less than 1. When products are favored, then the value of Kc exceeds 1. Now, the reason why temperature is the only factor that affects the value of Kc is sometimes difficult for students, but reactants already had a smaller barrier to cross. Now products which had a bigger barrier would gain more from this additional heat. So in this way, the chances of products becoming reactants increases. So this expression here, Kc, the equilibrium constant, is affected only by temperature, because changes in concentration and pressure would shift the position of equilibrium, but the change in the product and the change in the reactant would be relatively the same. So the value of Kc does not change. In the case of a catalyst, the equilibrium is not shifted. All that happens is that the energy of activation is lowered, so the rate of both the forward and the back reactions are increased. Here in the case of this reaction, esterification, Kc is equal to the concentration of the ester multiplied by the concentration of water divided by the concentration of alcohol times the concentration of acid. But what about the relationship between reactants and products before equilibrium is reached? Divide the concentration of reactants by the concentration of the products. Then this would give us a value that would not be Kc, the equilibrium constant, but it's referred to as Q, the reaction quotient. And if the concentration of reactants is divided by the concentration of products at any given point in time, then we determine Q, the reaction quotient, which at equilibrium equals Kc. Consider finally this reaction here. Concentration of reactants falls, concentration of products increases, and here at equilibrium, notice, it does not mean that you have an equal concentration of reactants and products, but at equilibrium, the concentration of reactants no longer changes and the concentration of products no longer changes.